So from this class onwards, we'll really be going into convex sets, convex functions, and convex analysis itself. So far, we were mainly discussing the prerequisites required to discuss these topics. And henceforth, I'll very closely follow the textbook by Boyd and Vandenberg. Again, the textbook is available freely online, and there are also hard copies available in the library. All right. So before we start, why are we so focused on convex sets and convex functions? Right, as we saw, a general minimization problem can be posed in the following way as computing an x star, which is the R min of f of x subject to some g of x less than or equal to 0. This was the class of functions, or this was a class of minimization problems that we were interested in. Now, and as we saw a very large class of problems, at least through some examples, we saw that many problems can be posed in this general form. Now, the problem is we are interested in solving these problems when the space of variables that we're optimizing over is very large, right? So we're not just interested in finding the minimum, but we also want to find these efficiently. So typically, we're interested where the number of variables involved could be at least a few thousands, maybe a couple of million. These functions could be complicated looking, and we want some kind, even a numerical method in order to be able to minimize the particular function subject to these constraints, right? So minimization of a function which involves several thousands of variables and maybe a few hundred constraints, right? So those are the class of problems that we want to be trying to solve. And in order to be able to do this efficiently, now, of course, you could try to focus on very specific classes of functions. And indeed, that is how the theory has developed. So for certain kinds of functions and for certain kinds of constraints, you have very efficient algorithms. So one very efficient or one class of problems for which you can solve these minimization problems efficiently, exactly, is the class of linear programming problems. Right? So this is the class of problems where f and g are both linear. So another class of problems could be the class of quadratic optimization problems. Right, where both f and g are typically quadratic. There are a class of programs called semi-definite programs. Wherein your constraints are in the form of some semi-definiteness constraint. So for example, the variables could be in the form of a matrix, right? You arrange the variables in the form of a matrix, and you want to minimize a particular function such that over the class of all variables for which this matrix is, let's say, positive semi-definite. Right? It turns out that many very important problems in computer science can be formulated as semi-definite programs. And for each of these, there are separate, very efficient algorithms to solve this, at least numerically. Right? But it turns out that all of these are specific subclasses of the more general class of convex optimization problems. Wherein f is convex and you're optimizing over a convex set. right? So then if this is the class of problems that we can solve efficiently, then what constraints do those imply on, say, g of x? So if I want a problem, if I pose a problem in the following form, wherein you want to find the minimum of f of x subject to g of x less than or equal to 0, wherein the constraint set is convex, then what property should g satisfy, for example? Or can I have a more general class of constraints beyond just g of x less than or equal to 0? Can I pose it in some other form? And again, what are the properties of f of x that allow us to solve these problems efficiently? Right. So it turns out that for this broad class of convex optimization problems, where f is convex and the constraints form a convex set, you can solve this minimization problem efficiently. Now, again, this does not mean that you can't solve more specific subclasses more efficiently. So, for example, if you know that it's a linear programming problem, then you could solve it much faster than using a general convex solver. Right? So this is a very general class which can be solved efficiently. But if you know that your problem lies in one of these classes, you could potentially solve it even faster. Right? So we'll see each of these problems. So what kind of sets, what kind of objects each of these are under the broad umbrella of convex optimization problem. Right? So we'll see what a convex set is. We'll see some other kinds of sets. Right? So there's another class of programming called, or class of optimization problems called conic programming and so on. There are various other subclasses of convex optimization problems that can be solved efficiently, and we'll see the basic mathematical principles underlying each of those. All right, so some of these tools that we develop are useful not just in convex optimization problems, but also in a variety of other fields. Right, so it always helps to get a basic understanding of all of these. All right, so we'll start with the very basic of what a line is. Right? So we are all familiar with the concept of a line in 2 dimensions, but what happens when we generalize it to general n-dimensional spaces? Right? So if I give any 2 points, x1 and x2, in general n-dimensional Euclidean space, then what would be the equation of the line passing through x1 and x2? Any guesses? Okay, for alpha. Yeah. So effectively, alpha x1 plus 1 minus alpha x2 for all alpha in R. So this is the line passing through x1 and x2. So firstly, it passes through x1 and x2. That is clear, right? Just by setting alpha equal to 0 or alpha equal to 1, you get x1 or x2, right? How do we argue that this is a straight line? Yes, sorry, who said this? Yeah.
So there is the interpolation between x1 and x2, so it must lie within the line joining the points x1 and x2.
What do you mean by the interpolation of x1 and x2? Okay.
That follow this would lie in that line which is joining the
Again, how do you argue that?
Is the differential and it has radius.
Okay, differential with respect to what? With respect to?
Like do it by doing expand, do it by x2.
Maybe one at a time. Yeah, you were saying something. Can you repeat?
Do it by do x1 plus do it by do x2. You should not have any variable.
Okay, again, what is a variable here? So right now it's a set, right? Yeah.
You can reread this as x2 but plus alpha takes x1.
Correct.
So the line is passing through x2 and its direction there is
Yeah.
x1 times.
Right. So I can write this as x1 plus 1 minus alpha times x2 minus x1. Right? So you can consider this as sort of a base point, right? You can consider this as a base and this as a direction. Correct? So for every alpha, I get a point which sort of starts from x1. If 1 minus alpha is positive, then it lies along it lies along the direction from x1 to x2. And if 1 minus alpha is negative, what happens? It lies in the direction opposite to x2. Right? So let's look at this in 2 dimensions. So I have a point x1 and a point x2. Right? So what would be the equation of the line joining or the line along x1 passing through x1 and x2 in 2 dimensions? What is the equation of the straight line that you're familiar with passing through x1, say x1 y1 and x2 y2? Yeah.
Y minus y1 equal to y2 minus y1 by x2 minus
So y minus y1 by x1 equal to y2 minus y1 by x2 minus x1, right? Can you have this equation? Can I rewrite it in the above form? Right? x1 plus 1 minus alpha, x2 minus x1. So again, you should keep in mind that these are vectors, right? In this case, x1 and x2 are vectors, whereas in this case, we have these spelled out in terms of the individual variables. So how do I write this in vector form? So effectively what I want is a formula for x, y, right? That's the vector. That's any point along the line x, y.
is the NT X minus C equal to 0, where N is the normal.
Sorry?
NT, N transpose, X minus C, X is the vector.
N transpose.
Bracket,
Okay.
X minus C.
X minus. Yeah.
X minus equal to alpha times x2 minus x1.
X minus x1 equal to
Alpha times x2 minus x1.
okay, x2
And
minus
similarly for y minus y1 would be alpha times
okay.
y2 minus y1. So that on dividing those equations, you will get our equation. And this can be written in matrix form as a similar equation as well.
So you agree that I can write x minus x1 as alpha times x2. So if I look at the set of all points in this particular form, right? So any x minus x1 equal to alpha times x2 minus x1, y minus y1 equal to alpha times y2 minus y1, then this satisfies this set of equations. Do you agree? Does everyone agree with this? Okay, now let's rewrite this. So in other words, if I view these as vectors, so I basically have two equations, right? And I can write this in vector form. The same two equations, which I've written as an equation in terms of a 2 by 2 vector. So again, if I rewrite, what happens? X, y equal to x1, y1 plus alpha times x2 minus x1, y2 minus y, which is simply x1, y1 plus alpha times x2, y2 plus minus alpha times x1, y1. Which is just x1, y1 plus x alpha times x2, y2 plus 1 minus alpha times x1, y1. Right? So what did we do? We started off with this particular equation, y minus y1 by x minus x1 equal to y2 minus y1 by x2 minus x1. Right? I just rewrote this in the form of a vector, but I also introduced this new parameter alpha. Right? So effectively what we have is the parametric form of the equation of a line. So by varying the parameter alpha from minus infinity to plus infinity, I get different points on the line. Right? And this nicely fits in the following form: xy equal to alpha x2 y2 plus 1 minus alpha x1 y1, which is alpha times vector x1 plus 1 minus alpha times vector x2. Maybe it's alpha x2 plus 1 minus alpha x1. Right? So in general, right, so that gives me the equation of a line which passes through x1 and x2. What about the line segment joining x1 and x2? So the line passing through x1 and x2 would be basically this straight line stretching all the way up to minus infinity and plus infinity. The line segment joining x1 and x2 is basically just this part of the line, right? So what values of the parameter corresponds to this? Yeah. So it's just alpha being between 0 and 1. Right? Any questions? Okay. So now we define what this notion of an affine set, right? Just as you had vector spaces, we want this general notion of a line and a set which contains lines. So we say that a set is affine if it's closed under straight lines, in the following sense. If x1 and x2 lie in the set S, then so does the straight line joining these 2 points. Right? So can you give me an example of an affine set? Let's take 2 dimensions. Okay, R2. Yeah. A straight line is definitely affine. Any straight line is affine. Okay, great. What about other sets? What about a point, which is a singleton? It's affine, right? The null space of a 2 by 2 matrix, which is what? Correct, but it's an even more. What does it look like geometrically? Is it any line? Is it any line? Correct. So it's a special case of the first example, right? So the null space of any 2 by 2 matrix is a straight line passing through the origin, or more, right? So either it's empty, or it is a straight line passing through the origin. Sorry, it's not empty, it contains the 0 vector. So it's either the origin, or it's a straight line passing through the origin, or all of R2, right? So in fact, more generally, any straight line, whether or not it passes through the origin, is affine. A singleton point, singleton set is always affine. R2 is affine, right? And as you mentioned, you said the null space of a 2 by 2 matrix, right? Can you generalize that a little bit further? You're right, you're heading along the right direction, but you can, there's a one more step of generalization to that. No, we're looking at R2, right? Linear combination of vector subspace, yes. So, okay, how do you define the null space?
That on multiply with the matrix result.
Okay, you're heading a slightly wrong direction. Any subspace is fine, but that again gets back to the null space, right? I want a generalization of a null space, which gives me an affine set, right? So, for example, I can't write can I write any affine set in R2 as the null space of a particular matrix? I can't, right? Because, for example, a straight line which is not passing through the origin is not the null space of any matrix. But again, how do you define the null space? Yeah, can you spell that out? It's the set of all vectors x which satisfy what? It's a solution of a system of homogeneous equations. So ax equal to 0. Okay, think along those lines. Yeah? Any system, the solution space of any system of linear equations, is that an affine set? I know, I'm trying to generalize that, right? So look at the solution space of any system of linear equations. So ax equal to b. Is this affine? So if x satisfies ax equal to b, right? Or I have two solutions, x1 and x2, which satisfy ax equal to b. What about alpha x1 plus 1 minus alpha x2? Is that also a solution? It is, right? So you look at, so x1 comma x2. Suppose that I have two solutions of this system of linear equations. What about alpha x1 plus 1 minus alpha x2? If I multiply this by a, what do I get? This is alpha ax1 plus 1 minus alpha ax2. But what is ax1 and ax2? B. So this is alpha b plus 1 minus alpha b. Right? Which is just b. So alpha x1 plus 1 minus alpha x2 is also a solution. Right? So it's closed under the line joining the 2 points. No, alpha can be any real number, right? Yes. It's not a convex combination. It's convex only if alpha is between 0 and 1.
The sum is 1.
No. So convex combination is, so alpha has to be between 0 and 1.
The system has to be.
So this is what is called an affine combination. There's a difference between affine combinations and convex combinations, right? The coefficient should all be positive, non-negative for it to be a convex combination. No, these can be negative, right? Alpha can be negative in this case. But yeah, they have to sum to 1. That's the only constraint. Yeah, you have. Yeah, if it has one solution, then there's only one x1. It's a singleton, right? It is affine, right? Is it closed? It's a single point, right? So automatically it satisfies this particular property. Right? So it is affine. So there's one more set, which is the null set. So the null set is affine. Every singleton set is affine. But beyond that, yeah, you need to check. Right, so in general, an affine combination of any set of points, x1, x2, up to xk. Let's say I take k points, alpha 1, x1 plus alpha 2, x2, and so on, plus alpha k, xk, where the sum of the coefficients is equal to 1. That's called an affine combination. The alphas need not be between 0 and 1. They could be negative. They could be as large as possible. Right? But they all have to be real and they have to sum to 1. So in other words, an affine set is one which is closed under affine combination. Okay? And in fact, every affine set has this nice property that it's always a shift of a vector space. All right? So let us look at in this case. All right? At least in R2, right? The only non-trivial affine sets that we could think of were straight lines. So it's either empty or it contains a singleton or all of R2. These three are affine anyway, but these are what I call trivial affine sets. The only non-trivial affine set was a straight line. Every straight line is affine. But the straight line will not pass through the origin. Right? And what is any vector space of dimension 1 in R2? So line passing through origin is the only sort of non-trivial vector space, or it's a vector space of dimension 1, right, in R2. And you can view every straight line as a shift of a straight line passing through the origin. Correct? So in particular, let me take any affine set. Okay? Okay, take any affine set. And I'll take any vector from it. Doesn't matter which one you pick. Let's say C is in S. I claim that this set S minus C. So basically I shift all the vectors in S by an amount C. I claim that this is a vector subspace. How would you verify this?
Zero vector is part of the set.
Okay. So zero vector is certainly part of the set, right? Again, what's a simple test to check whether a given set? So basically it has to be closed under linear combinations, right? So what I want to show is that if I take any 2 points, let me call them, so every point can be written as some x1 minus c and x2 minus c, right? Where x1 and x2 belong to S, correct? So x1 minus c and x2 minus c are going to belong to this set S minus c. And I want to show that if I take any linear combination of these 2 points, not necessarily affine, right? Any linear combination, that point should also belong to the set X minus c. So let me take any linear combination, alpha times x1 minus c plus, let's say, beta times x2 minus c. Can I write this as some point from S minus c?
Alpha and beta and expand.
Sorry?
Expand this.
Okay, fine, let's do that. So let me write, so this is alpha times x1 plus beta times x2 minus alpha plus beta times c.
You know that beta x2 belongs to S.
No, we don't know that, right?
X2 belongs to S.
X1 and x2 belong to S, but only an affine combination of x1 and x2 belong to S, right? Affine combinations of more than 2 points also belong to S. So remember, right now we have 3 points, right? We know that x1 belongs to S, x2 belongs to S, C also belongs to S, because that is how we chose C, right? C is another point. So I know that every affine combination of x1, x2 and C also lies in S. Is this an affine combination? Sum is what? So we add a C and subtract a C, right? So I can write this as alpha x1 plus beta x2 plus 1 minus alpha minus beta C minus C, right? I just added and subtracted the vector C. So this is, I have a minus C as required. What about this first part? Is this in S? It does, right? Because alpha plus beta plus 1 minus alpha minus beta is equal to 1. So this is an affine combination of x1, x2 and C. Right? So effectively every affine, so no matter, we started with an arbitrary affine set, right? You take any vector from the affine set, subtract all the vectors from the affine set from this, you get a vector space. Right? So one way to view an affine set is basically that it's just a shift of a vector space. So there is this equivalence between affine sets and shifts of vector spaces. So this naturally gives us the notion of the dimension of an affine space, right? Because you can write every affine space as a shift of a vector space, the dimension of the vector space is basically the dimension, is what we call the dimension of the affine space. It's a definition. So effectively, when you're solving linear programming problems, when your constraints and your function is basically linear, well, effectively it's not linear. Typically you choose your constraints to form an affine set, right? It's a bunch of linear inequalities, and your function is typically taken to be linear. The objective function is linear and the constraint set is chosen to be affine. Right? And in fact, every affine set is the solution space of a system of linear equations. Why is that?
System of linear equations that are basically the lines or the geometry passing from the origin are a set of linear equations. You shift those to.
Correct. So what is the solution space for a system of linear equations? Okay, in 2 dimensions, right? So in 2 dimensions, the solution space is not always a line. Yeah, so it's either, yeah, it's an intersection of lines. So it's either empty, or it can consist of a single point, or it could be all of R2, or it's a straight line, not necessarily passing through the origin. So at least in R2, we see that it's fairly clear that every affine set that we can think of is the solution space of a system of linear equations. But how do we make this claim more generally? In Rn, every affine set can be written as the solution space of a system of linear equations. Well, let's just use what we just saw, right? Every affine set is the shift of a vector space. Can we use this?
It's the solution of a homogeneous system.
Yep.
And so we shift it to get a linear general linear system.
That's it, right? So what do we have? So every affine set can be written as some vector space plus a shift, right? Do you agree? Any questions? So just based on what we saw, every affine set can be written as the vector space plus a shift. But I can write every vector space as the solution to a homogeneous system of linear equations. Okay, so that means this is the same as the set of all x such that ax equal to 0. Right? So there is some A, right? Some matrix A for which V is basically the null space, the right null space of that particular matrix. Everyone agrees with this point? Yes? No? Okay, so from this, how do I get the affine set? Or how do I say that this is the solution space of the system of linear equations? Yeah, so what is S basically? It's a set of all x plus b. So it's the set of all x plus b such that ax equal to 0, x such that, or maybe let me change the variable here, or right? Any questions? Yeah.
The dimension of X and B is necessary. It's not necessary that they would be same, right?
Why not?
So what if A is not a square?
That's okay. So it's AY equal to AB, right? So X lies in Rn, X and Y and B all lie in Rn, right? But AY and AB could lie in some Rm, where N could be different from N. That's okay. Because in principle, it doesn't matter because all we're interested in is the right null space. So as long as the dimensions match, the size of the number of rows in it don't really matter, if you think about it. Any questions? Okay. So similarly, we define this notion of an affine hull. So given an arbitrary set, what is the smallest affine set which contains this particular set? So given a set, let's call it C, the affine hull is basically the set of all affine combinations from C. So in some sense, this is the smallest affine set. That contains the set C. So let's take an example. Suppose I have a set which consists of only 2 points. What is the affine hull going to be equal to? It's going to be the line passing through these 2 points, right? So if we have, again, it should be close. So the set of all affine combinations of all possible points, right? So if I have only 2 points, then it's basically the straight line joining these 2 points should be in the affine hull, and therefore it'll just be a straight line. Now, say I pick a third point. What will happen to the affine hull? Yeah, so let's just take R2. Okay, we're focusing on R2. So if the third point lies along the line joining these 2 points, it's the same thing, nothing changes. If I pick a third point which is not in the line joining these 2 points, it contains all affine combinations. So mind you, take any 2 points in the affine hull, the straight line joining those 2 points should lie in the affine hull. Correct? So suppose I pick a third point somewhere outside. So what does it mean? Every straight line joining this point and every point along this line should also be contained in the affine hull. Right? So what does that mean? What will it be? It will be all of R2. Do you all agree? So another way to think about it is how many linearly independent vectors are there. So you pick any point in this set, right? In this set C, take any point. The affine hull will contain this set. So if I shift the affine hull by this point, I should get a vector space. Correct? So now how many linearly independent vectors are there in this particular set? So again, by linearly independent, I'm sort of shifting the origin. Right? You should think about it in the following form. So I have, say, 3 points. I make one of these points my origin. Pick any arbitrary point, doesn't matter which point you pick. So I pick one of these points as the origin, and I look at the vector space that is generated by the remaining points. I get some vector space. I shift that vector space by this particular point. Let's call it, let's say that this is my x0, 0 to denote that this is going to be my new origin. I have this bunch of points which form my C, right? So I have this vector, I have this vector, I have this vector, and this vector. Right? So what is the dimension of the vector space that is spanned by these vectors? In this case, it's going to be 2. That specific example that I had. Right? So in many cases, we'll be interested in optimization problems where our constraints are basically affine sets. Right? And so if you think about a general optimization, convex optimization problem, right? Let's think about what our intuition says in one dimension, functions on R. Suppose that I have a particular constraint, right? And this constraint, let us say, is in the form of an interval. Okay, so I have a general function f. I want to find R min f of x, where x lies in some closed interval a comma b. What can you say about the minimizing point? okay, it should lie within A and B, but then what more can I say? There are two possible cases, right? So suppose that, well, there are two problems here. One is there's an unconstrained problem, right? This is my original problem, problem 1. I have a problem 2, which is just argmin f of x. Now remember, my f is a convex function, right? Which means that how many points of minimum are there for f of x? 1. There's only one. There's a unique minimizer if I look at the unconstrained optimization problem, right? But now I'm imposing this constraint, so something else might happen. So geometrically speaking, I have this particular function, right? And there is an x star, which is the unconstrained minimizer. Now what can happen? I have this, now I'm imposing a constraint, so I want x to lie within A and B. I'm looking only for the minimizer between A and B. Now if the interval a comma b includes x star, then what is the minimum? It's equal to x star. The minimizer is still x star. So that is when this is A and this is B. But that may not always happen, right? It could be that the interval a comma b is either to the left of x star or to the right of x star. So suppose, without loss of generality, I'll assume that it's to the right of x star. Then what happens to the minimizer? Yeah, so it's going to be minimum of f of a and f of b, whichever is the minimum of those two, right? And that's especially because we've chosen this function to be a convex function, right? So let's again try to think about it in 2 dimensions, right? A convex function is in the form of a bowl, right? And I take some constraints. Maybe my constraint is in the form of, let's say, a convex polygon. Just think of it as a rectangle, okay? My constraint set is a rectangle. I want to minimize the convex function, right? So now it's like this sort of a bowl, and I'm minimizing this in some rectangular region. Okay, so this is the set for which I'm looking for the minimum of this particular function, right? So if the unconstrained minimum lies in this particular set, it's fine. Otherwise, what can you say about the minimizer point? Where will it lie? Intuitively, yeah? It's going to lie in the boundary of this particular constraint set, right? It has to lie in the boundary, right? Because it's a convex function. If it lies inside, then it means that the true minimizer should lie inside that particular set. Otherwise, the minimizer is going to be some point on the boundary of this particular set. Right? Do you all agree? Again, we're just trying to build up intuition over here. At least in 1 and 2 dimensions, we can see that the minimizer is always going to lie on the boundary. In fact, this is going to be true irrespective of which Rn you go to, what irrespective of the value of n. If you look at any convex function on Rn, the minimizer is either, as long as it's nice, smooth, convex, and so on, the minimizer is either going to be an interior point, it's going to lie strictly within the constraint set, or it's going to lie on the boundary of this particular set. All right? But then how do we define the interior and the boundary of the set? So if these are functions of Rn, we've already defined what the interior of a set is, what the boundary of a set is. But that assumes that the sets that we're considering sort of have the same dimension as Rn. Right? So for example, we're working with R3. We're assuming if the constraint set already is a set of dimension n, then it's fine. But for example, I have this function on R2, but my constraint set need not be sort of a two-dimensional region. It could potentially be just a line, right? Maybe my constraint set corresponds to just one straight line. This is the set of all possible x which satisfy these constraints. So now I'm sort of going down from a higher dimension down to a lower dimension. So for this, I define this notion of a relative interior of a particular set, right? Because I want the notion of interior, but now in a lower dimension than the dimension of the original space. My set S, which could be the set of constraints, could be a higher dimensional set. It's a subset of Rn. But when I look at the constraint set, turns out to be a lower dimensional set than what was originally there. Right, so the relative interior of a particular set. So what do? You look at the affine hull of this particular set. So for example, let's go back to this particular example that we had, right? Suppose that my original constraint set was a rectangle, right? A closed rectangle. What would be the interior of this particular set? Exactly. So it's basically the open rectangle, right? So all the points except the boundary. And what is the boundary in this case? So suppose I have, let's say x1 less than or equal to a1 less than or equal to b1, x2 less than or equal to a2 less than or equal to b2. This is my set, right? What is the interior of C? X1 is strictly greater than A1 but strictly less than B1. X2 is strictly greater than A2 but strictly less than B. Right? This is an open set. The interior is an open set. And what is the boundary? Is it just A1, B1 and A2, B2? So think about it pictorially, right? What does this set look like? Let me write. This is my axis. Okay, this is my x1 axis. This is my x2 axis. This is A1, B1, A2, B2. So the set is basically this particular rectangle, right? This entire rectangle. What is the interior? What is the boundary of this particular set? It is just a union of these line segments. Correct? And how do you represent this? Yeah?
Combination of the
Correct. So it's Any convex combination of the 4 points?
The vertex convex combination.
Correct. Is it any convex combination of? Is it a common combination of every pair of vertices?
Edges.
So it's only convex combinations of adjacent pairs of vertices, right? So it's a convex combination of these two vertices, these two vertices, these two vertices, and these two vertices. In fact, it's a union of convex sets, right? Okay, but now if I look at R2, right? What is the interior of, let's say, a line segment in R2? So, okay, we're looking at R2. Okay, my set in R2 is basically the line segment, some line segment. Okay, what is the interior of a line segment in R2? Yeah, empty. Right? It's going to be an empty set, because remember, what is the interior? An interior always has to be an open set, right? And what is an open set? It has to contain a ball of some radius, right? You can't draw a ball of a two-dimensional ball of non-zero radius, which contains this, which is contained in the line segment. So in this case, the interior, this is my C prime, interior of C prime is the null set. But I still want to be able to define a notion of interior, because no matter what kind of a constraint set I have, I want to know what my boundary is, because these are sort of the points which could potentially be my points of minimum or the interior. So my minimizer is either going to always lie in the boundary or it's going to lie in the interior. If it lies in the interior, then that's going to be the unconstrained minimum. If it lies on the boundary, then it's not the unconstrained minimum, or need not be the unconstrained. Right? So in order to circumvent this kind of issue, wherein my constraint set could be of a smaller dimension than my original space, we define this notion of a relative interior. Right? So this lies in some affine space, which is potentially of a smaller dimension. So you just you look at balls of that particular dimension. Right? So if you look at, let's take a ball centered at x of radius epsilon. Now this is an n-dimensional ball, but I take the intersection with this particular affine set. Right? Now that's going to be a smaller, it's going to be a ball, but in smaller dimension. So think about the following. So you take a ball, let's say a three-dimensional ball. I take the intersection with a plane. What am I going to get? It's going to be a circle. Right? It's going to be some circle. So this is what I'll take as my new ball. That's my proxy for the original ball that I have. So as long as this is contained in C, for some positive epsilon, then it lies in what I call the relative interior. So for example, in this set C prime, what is the natural notion of the relative interior? Correct. So it's a line segment excluding the endpoint. Right? That would be the notion of sort of the interior of this particular set. And indeed that's what we're going to choose. So that is what is going to be the, if you again apply this particular definition, you will get basically the line segment excluding the endpoints. And what is a boundary? It's just the closure minus the relative interior. Okay, so far what we looked at were affine combinations, right? Any linear combination of points where the coefficients all sum to 1. If in addition you impose that all the coefficients must be non-negative, then it's called a convex combination. So alpha 1 x1 plus alpha 2 x2 so on alpha k xk equal to 1 and alpha I is greater than or equal to 0 for all I. This is called a convex combination. Of x1 up to xk. And a set is convex if it's closed under convex combinations. And similarly, just as we defined the affine hull, the convex hull is basically the set of all convex combinations of the given points. So now let's go back to R2. Right? Suppose I give 2 points. Remember that the affine hull of these 2 points was basically the straight line joining these 2 points. What is the convex hull of these 2 points going to be? It's just the line segment joining these 2 points. Now, if I take a third point, it's going to be the triangular region which is enclosed by these 3 points. In general, if I take 4, 5 or a constant number of points, what will it be? It's going to be some polygonal region. Right? But more generally, it could look more complex. Right? So can you give me an example of a convex set which cannot be generated as a linear combination of finitely many points? Circle, right? A circle or an ellipse, right? So you can't write this as the convex hull of finitely many. Right? So one difference between one key point to note is that unlike an affine hull is essentially going to be an unbounded set, right? Because it contains the entire straight line joining any 2 points. The convex hull, if you have a bounded set, the convex hull is also going to be a bounded set, right? Any questions so far? Yes.
There are two sets, let's say A and B.
Okay.
So that A intersection B is 5.
A intersection B is empty. Okay, fine.
And the convex hull of A is, let's say, A1.
Just one. Okay, so you have A and B such that A intersection B is empty, and you have whatever convex hull of A and convex hull of B. Yeah,
Say set A union B.
A union B. Okay,
A union B would be the convex hull of A union convex hull of B.
we'll get to this a little later, but what do you think will happen? It should be. Okay, we'll get back to what happens to unions and intersections of closed and convex sets and so on, right? But so firstly, if A intersection B is empty, does it mean that the convex hull of A and convex hull of B are disjoint? Not necessary, right? Because I could always, I mean, take a finite set. The convex hull, so for example, if I take, let's say my A is these 4 points and my B is, let's say, these 3 points. The convex hull of the convex hull of the white points is going to be this rectangular or whatever polygonal region, whereas the convex hull of the orange points is going to be this triangular region, right? So right now, coming to your answer, what is the union of the convex hulls? Correct, union of these two. But what is going to be the convex hull of the union of these points? There's some more region, right? So firstly, the union of the convex hulls, is it necessarily a convex set? No, right? So we'll see later on this can be generalized, that the union of two convex sets is in general not convex. The intersection of two convex sets is always convex. So in this case, the union of the convex of, in this particular example, the union of these two convex hulls is not convex at all. But the convex hull of the union is always going to be a convex set, right? So in general, the union of these two is not equal to the convex hull of the. Okay. All right. So one last point. So this notion of convex combinations is sometimes generalized to more than just finite combinations, right? So if I give you x1, x2, xn, and so on. So if I take an arbitrary set C, then you could potentially even look at infinite linear combinations, alpha I, xi, equal to 1. Right? So this notion of convex combinations can be generalized to infinite linear combinations, as long as, of course, this exists. Right? In general, this convex combination may or may not exist. It may not converge. Right? It's after all an infinite sum. Right? It sometimes can be generalized even further, not just countably infinitely many points, but even uncountably infinitely many points. So For example, you take any uncountable set C and you take any probability density function on C, right? So what can you say about integral x in C, f of x dx? What will this be? Yeah, it's 1, right? It's a probability density function on C, right? What is integral x in C? X times f of x. Yeah, it's an expectation, but it's also a convex combination, right? So one way to view this, in fact, is that you look at alpha i's. The alpha i's form a probability mass function, right? It's just a PMF because all the alpha i's are greater than or equal to 0 and they sum to 1. So it's a valid probability mass function. And the xi's are some numbers, right? You think of the alpha i's as the probabilities of those numbers occurring, then essentially a convex combination is just the expectation of x under that particular probability mass function, right? So similarly, so every convex combination is effectively the expectation of, can be thought of as the expectation of some random variable, right? Where the probability distribution or the probability mass function essentially corresponds to this coefficient of the convex combination, and the xi's, the points whose convex combination you're taking, are basically the realizations of that random variable, right? That's your sample space, right? Okay, so let's stop here. Any questions?